Okay, today area is in the plane, part 2. So we're just going to take things up a notch a little here. But I don't want you to be afraid. This is one of my favorite lessons of the whole year because it looks like we're delving into some really tough stuff. And then there's a really smooth way to handle this situation that makes it nice and easy to handle. And it's not tough thinking at all. Like, it's just a little bit of extra thought that we got to put into these questions. Okay, boundaries with changing functions. When finding areas, we sometimes need to partition the area, the region, into subregions. It says find the area of the region in the first quadrant that is bounded by y equals root x bounded above by y equals root x, and below by the x-axis and the line y equals x minus 2 by partitioning the region into subregions. Okay, so I got enough room here for a little sketch of the situation here so you can see what's happening. And so I'll just get the first quadrant in here so you can really see what's happening. You can put this on your graphing calculator if you really want to see what's happening. But so y equals root x is going to have some kind of shape like this in the first quadrant, yes? And then y equals x minus 1 comes up from below. It doesn't get to the x-axis to a value of 2. I'm going to put that on there. And then it sort of comes up like that, and they meet. You could do that with a table of values pretty easily. You can do it on your graphing calculator, no problem. But there's the situation. So if you want, there's the line that goes down like this. So let me just label these things so it's clear what's happening. There's y equals root x. And here, this line here, is y equals x minus 2. And what they want is to find the area that's bounded above by the red line you see there, the red curve, y equals root x, and below by the x-axis and the line y equals x minus 2. Now, here's what's happening is if I just draw a little dotted line down here, and this is the really important part of this lesson, is the lower function changes as we go along here. For a while, the lower function is just the x-axis. We don't usually think of that as a function, but that's the function in this case. And then once you get to a certain x value, then the lower function becomes y equals x minus 2. So you got to partition this area into two pieces to be able to find its area. And you really got to know a lot about the function. You got to have a nice little graph of it to be able to do these calculations. And we need to know a couple of things. We need to know where these two functions meet. So first of all, we need to know when does root x actually equal x minus 2. And I got to square both sides here. And if you've never squared both sides to solve an equation, when you do square both sides to solve an equation, there's an extra step here, and I'll show it to you in just a second. Multiply out those brackets, bring over the x, and everything seems fine. But you can see I'm not looking for both those answers. Once you square both sides, you're sort of stuck with having to check the answers and sub them back in to see if they work, because you introduce incorrect solutions when you square both sides. Basically, what you do is you turn negatives into positives, and then things that weren't equal become equal. So if you look at this equation, if I sub 1 back into the original equation, an x value of 1 there, you'll see that root 1 and 1 minus 2 is 1 and negative 1. This doesn't work. I've introduced a wrong solution. That's a different kind of error than any other situation. When you square both sides, you got to check the answers. But when I sub the 4 in there, it does work. You get root 4 is 2, and 4 minus 2 is 2. So that does work. So where do these meet? At the point 4, comma 2. I sub the 4 into the root x or into the x minus 2 to get the y value. So now I know the coordinates at that point. To get the coordinates, this point is a little bit easier. That's the point 2, comma 0. I want to know when it hits the y-axis, and that's when the x value is 2. Okay, so now I've got my values to do this area. So what I want to do is to find this area I'm after, I first got to find the area from 0 to 2, and in that section I'm going root x minus nothing, because there's what's below it, the y equals 0, so we're subtracting nothing off of there. And then the second part is from x value 2 to 4, and in that section, I'm actually going root x minus the x minus 2 function. So you see the lower function changes during this area calculation or during this integral, what is the lower changes, and that really makes it so you have to divide this into two sections. Okay, so let me just tie this up a little bit. I get area from 0 to 2 of x to the 1/2, and area from 2 to 4, let's go x to the 1/2 minus x plus 2 dx. And the rest of this is just antiderivatives and so on. So not really a big deal what has to happen here. So I need, let's see, x to the 3/2. So that's going to be a 2/3 out front. And that's from 2 to 0. And then, again, this 2/3 x to the 3/2 minus half x squared plus 2x. And that's from 4 to 2. So I got a lot of crazy subbing in to do to get these two different answers here. Okay, first one, sub in 2 into that thing. So what I get is a times 2/3 times 2 to the 3/2 minus 0, because when I sub in 0 to that thing, I get a 0, plus the first set of brackets for this one, I'm subbing in 4. Okay, so when I put in 2/3, now it's 4 to the 3/2 minus 1/2 of 4 plus 2 times 4 minus, when I put 2 in there, I don't get 0 the whole time. I get a whole bunch of other terms here. I get 2/3 2 to the 3/2 minus 1/2 of 2 plus 2 times 2. And that's all in that second bracket there. Got myself some more space down here. This thing's a mess. 2/3 2 to the 3/2. Let me just deal with that in a second. But in this bracket here, 4 to the 3/2. So the half in there is square root. So I'm taking the square root of 4, which is 2, then putting that to power 3, which is 8 times 2/3. That's 16/3. If you need more than one step there, you can go ahead and do that. Half of 4, oh, I know what that is. That's minus 2. And then plus 8. Oh, I wasn't careful with my brackets here, was I? Okay, so that was the first bracket. Minus, there's the whole second bracket. So I get this minus 2/3 2 to the 3/2. And minus, okay, this is minus a half, but it's minus a half, so plus 1 and a minus 4. Just looking those over to make sure I got all those things in there right. Oh, this was a 1/2 x squared up there. 1/2 x squared. So that's not a 4 in there. When I put a 4 in there, that's a 16 in there. Plus 2 times 4, that's right. And then the other brackets, that's right. Minus 1/2, 2. Ooh, that's a squared right there. Plus 4. So how's that's going to change over here? That's right. 16/3 is right. Minus 1/2 of not 16. That's a minus 8. And then in the second brackets, 1/2, that's a 2. An important little thing that happened to me there. I think it's important every time you do a line, especially when these get longer and longer. You don't want to go back and check your work when it's all done, because you might have 5 or 6 lines of bad math there. I think it's important to scan over each line and make sure that they're right before you move on, and that's what I did there. So, a good thing has happened, though. I got the 16/3, but the 2/3 2 to the 3/2 combined with that later 2/3 2 to the 3/2, which was subtract, so that just goes. The minus 8 and the plus 8 go, and plus 2 minus 4 is minus 2. And so what I get area is 16/3 minus another 6/3. I get area of 10/3. So except for my little forgetting a squared mistake there, not a bad question overall, dividing that into two sections. But you do got to draw a little graph there, or use your graphing calculator to get a little graph of it to see what's going on. Yeah, the algebra around finding intersection points is valuable because then you know where these things happen. Now, I guess that really could have been part of last day's lesson. And I'm going to show you something now that is really what this day's lesson is all about, and actually makes this question easier. It says, is there a slightly more efficient approach? Well, why this got so convoluted was because there was two separate integrals that had to be done because the lower function changed. It went from y equals 0 to y equals x minus 2. And when a lower function changes like that, you got to break it into different pieces. Is there a way to do this question without doing that? Is there a slightly more efficient approach? Well, if you're watching this on a screen or an iPad or something like that, just turn your screen sideways for a second. And I'm going to turn my head sideways. And I want you to notice, I'm going to try and draw in a weird color here, is that if I had done this sideways, you see the upper and the lower stay the same all the way through there. The upper, the right-hand function is y equals x minus 2. The lower, the left-hand function is y equals root x. So we wouldn't have these two sections if we had thought about this in the y-axis instead, like it's thought about it on its side. Now, some people think of it as right minus left, and that's a great way to think about it. And some people just put their head sideways and just change what they think upper minus lower is. So the answer to the question, is there a slightly more efficient way? And again, after all this, you might be like, well, do I need something that's slightly more efficient? In this particular question, it's slightly more efficient. As the integrals get more complicated, it might become impossible to do it one way versus the other. And so you're going to need this extra weapon, which is integrate with respect to y. And I'll put an exclamation mark and a question mark. An exclamation mark being, what a great move to turn this into right minus left instead of top minus bottom. But then a question mark like, how would this all play out? What are the details of this? And I'm going to talk a little bit more about it and then do an example to hopefully show off what, or I'm going to do this example, in just a minute. But I just want to talk a little bit more about what we have to accomplish first. So if you look at the diagrams below, it is sometimes more reasonable to describe the boundaries of a region using the functions of y instead of x. Take a look at these three things. If you try to do integrate this with respect to x, especially that first one, you'll see that the upper and lower, like it changes so many times what the upper and the lower is along this function, and even has multiple sections of upper and lower. Like as soon as the function gets complicated at all, good luck doing it with respect to x because the upper and lower keeps changing. But notice if you do it horizontally, do you see the right and the left is constant? The x, the f function is always the right-hand function, and the g is always the left-hand function. Now, it won't always be this simple, but you want to have this other weapon available that you're going to integrate this with respect to x instead of with respect to y instead of with respect to x. And all you're going to do is just, the big thing is you've got to get it as a function of x instead of a function of y. So you've got to solve for x, decide what's right and left, and then go from there. So it says, determine the area in region 1 by integrating with respect to y. So I'm going to redraw that picture down here. Here was my picture. Something like that. And something like that. And let me just get a few points labeled on here that we're going to use. This point here was 4, 2. This was y equals root x. This was y equals x minus 2. And I've sort of left some space there because I'm going to change that, what they're called in just a second. And this was the point 2, 0. And this was the point 0, 0, although that wasn't an important point in the other method of doing this. So now I want to change what I'm going to call this thing. I'm going to square both sides, and this thing is actually called x equals y squared. That's what that function is it's x equals y squared. And then the bottom function, actually, I've got to move that 2 over, and this is really called x equals y plus 2. Well, it's not really called x equals y plus 2, but if I want to do it as x equals, then I've got to do it as, I got to move that 2 over and isolate x. Okay, so now I've got those things labeled as x equals functions. And now what I'm doing is I'm going right minus left instead of top minus bottom. What I mean by that is when I do the integral, I'm going to take the top function, which is going to be the right-hand function here. And the right-hand function is y plus 2. And I'm going to subtract the bottom function, which in this case is the left function. So it's right minus left, and that's y squared. See, all in terms of x. So now I'm going to do my integral with respect to y. So I need my two y values that I want to integrate from. And the two y values I'm going to integrate between are 0 all the way up to y value 2. And if that seems weird, let me just draw this on here. There's y value 2. There's the two y values I want to integrate between. I want to go from y value 0 up to y value 2, and I want to take the upper function, which is x equals y plus 2, and subtract the lower function, which is y squared. And this may look weird at first, because you're so used to x's, but in the end, it's the same. Well, there's my limits there, 0 and 2. In the end, it's just the same as working with x's. Let's see. Antiderivative of y is y squared, 1/2 y squared. Didn't forget the squared that time. Antiderivative of y is just 2y. And the antiderivative of y, negative y squared, is negative 1/3 y cubed. And I'm doing that between 0 and 2. And so I put in the 2 there, and I get 1/2 of 4. So I get in the first bracket 2. Oops, I don't know why I put a comma there. Plus a 4 minus an 8/3 when I sub those in there in the first brackets. And in the second set of brackets, I get nothing. And 6 is 18/3, subtract 8/3, which is 10/3. Wow. Wasn't that simpler? Now, I understand this, that setting it up the first time is weird. Just think in terms of x equals instead of y equals. But I think you'll get used to that pretty quick after you do a couple of examples, and just either turn your head sideways and think upper minus lower that way, and it works nicely, or you can just go right minus left and keep your head the same way, and that works fine. Okay, last example. It says use a calculator to find the area of the region enclosed by the graphs y equals x cubed and x equals y squared minus 2. Now, I did this with Desmo so I could import it in here nicely, but you can do it on your graphing calculator, no problem. You can see what my window's sort of set at there, like sort of like -2 to 2 and like -2 to 3, and you'll get a nice graph like this of these two graphs, y equals x cubed being the red graph. Now, Desmos allows me to enter it as x equals y squared minus 2. Most graphing calculators don't allow you to do that, so you'd have to instead solve for y, which is move the 2 over, and do the positive and negative square root to get this whole function. Now take a look at this situation once you've got that all graphed, and I put the intersection points on there because I'm going to need them in a minute. This question says use the graphing calculator, so I just went ahead and used the calculator to do it. If you're doing it on your graphing calculator, you'll have to find the intersection. So click, with the graph on the screen, click intersection and find the values for those 2 points. Now, I could do this with respect to x. If I do that, I'll be going upper minus lower, and notice what happens. The lower function changes as I go along there. For a while, the lower function is the blue one, then it becomes the red one. So that will work. You can break it into 2 sections and do that. But if you do it with respect to y, then you're going right minus left, and notice how the upper and the lower stays the same all the way through. The upper is the same all the way through, or the right-hand function, and the lower is the same function all the way through. And that makes things just a little bit easier when you do that. Now, I just want to mention that if I'm going to then do this with respect to y, as I've decided here, I've got to rename these functions in their x equals names. Yes? So the x equals names of these things, well, this one, the red function, which is y equals x cubed, I've got to do cubed root, and so what I get is y to the 1/3 equals x. So this function here is x equals y to the 1/3. All I've done is isolate x. That's really the same equation. And this function here, which was x equals y squared minus 2. Oh, wow, they already gave me that in just the exact terms I wanted, x equals y squared minus 2. You see, we're just trying to open our minds up a little bit and say, it doesn't have to be y equals. x equals will work just fine. So then I want to take this integral, the area, and I'll do the limits in just a minute, the limits of integration, because that may seem a little bit weird. But I want to do right minus left, if you're thinking that way. Or upper minus lower, but turn your head sort of sideways so that you see what the upper and the lower is. So it's y to the 1/3 minus the lower, which is y squared minus 2. That's all in brackets. And we're integrating with respect to y. If we're integrating with respect to y, that means we want to start at a lower value of -1 and get all the way up to this estimated value of 1.793. The decimals only does 3 decimal points. If you want more accuracy, you can do that. It's not too hard to come up with that number on a graphing calculator. I've got it on my page here, 1.793003715. So that's what I'm going to use here. Because I think you're probably using your graphing calculator. That's probably the y value you'll come up with, is negative 1.793003715. How much difference in the answer will you get? Well, not much, really. Now, I like simplifying these brackets before I get going. I don't like little mistakes, as I just made there. I don't like the little mistakes that pop up when you're not careful about these things. So I'm going to do an extra line here and go y to the 1/3 minus y squared plus 2. So easy to make a positive, negative mistake so you're not careful with those things. Now, this thing doesn't say to do it. It says use the calculator. So I don't need to go through and do the antiderivatives here, which I could. This one isn't impossible to do with just antiderivatives. But if you just type it in your calculator, and I'm going to do it here and say the steps out loud because I don't have a graphing calculator on the screen. So on the Casio calculator, I go menu 1, and I get into my graphing calculator. And if you're not in math mode, you got to get into math mode. So you'd go up to setup, and where it says input output, you'd want it into math mode. So you'd press F1 to get it into math mode, and then exit out of there. And then when you do that, along the bottom, you'll see these options: jump, delete, mat. That's for matrices for later on. I mean, in university type courses. And then the math button, which is you press F4. And when I press the F4 button, I get some options, but the one that I want is one menu over. So I got to press F6 to arrow over, and then I get my integral button. How nice. It's as a dx. So I'm going to use x's to type into there. The calculator doesn't really know what I'm up to, so I'm using the variables of x in replacing y here. So I need what? X to the exponent 1/3. Minus x squared plus 2. If I press right arrow, then I get to the lower limit of integration, -1. I press right arrow, I get to the upper limit, which is, why do I keep saying -1.79? It's not -1.79. Positive 1.79 is what I'm after there. Yeah, okay. So 1.793. If you use what I did off Desmos, if you use your graphing calculator, you probably got more decimal places. So 0.03715. I think it's all in there. And when I press enter, that is a tough integral for the calculator because it takes a minute. It thinks it over. It's doing some work there to come up with the answer. So while it's doing some work, I go A equals down here. And eventually it comes up with the answer. And I'll write all the decimal places just in case you're right with me with the calculator so you can see if you get the same thing. I get 4.214943561. Okay, so upper minus lower? No, right minus left maybe, if that works better. And you need the graph sometimes to be able to pull off exactly what's happening here and know which way is the better one to use. How will you know which one's the better one to use? Look at the upper minus lower, and if either the upper or the lower function changes over the area you're trying to find, then maybe the other choice will work better. And then you go right minus left, and then you go over the y values I'm looking for. Does the right minus left of those functions stay the same? And if they do, you'll find it easier to do with respect to y instead of with respect to x. If you're doing that, make sure you have both functions as x equals, and you'll be off to the races. Great practice questions today. Mow your way through them. Have a great time.